quick sound check for those of you who are on the stream. Um, you post a quick chat message acknowledging video and sound, please. According to my tech, everything should be fine, but things happen. Great, thank you. All right, we're almost ready. Let's give a few minutes to folks who might be joining a few minutes late. So we'll get started in Lunar New Year. I have a couple of folks at my company took the day off to celebrate. Wish I would have done that, but didn't schedule a day off, and plus I still have to be here for all of you. So. Alright, so hopefully this gets fixed soon. YouTube is not receiving enough video to maintain smooth streaming. As such, viewers will experience buffering. Alright, so hopefully when I stop my music, it will get better and it's not choppy for you all. Let me do that actually, just to see if things get better. Okay, Google, stop. Maybe that helps. All right, hopefully. All right, let's get started. This YouTube is telling me that it's not receiving enough video. I'm not sure what that means. Hopefully the video gets smoother now that my kids will stop their schooling for lunch. It's actually a good thing that this is scheduled at lunch. Okay, so folks are experiencing buffering. Okay, so hopefully this gets better. I'm not sure what else to do here. It's set to like the max. Oh dang it! No, I think it's on my side because YouTube is telling me that it's not receiving enough video to maintain a smooth streaming, which so it must be my streaming to YouTube. But I don't have anything else to play around with to make it better. All right, so let's hope that it gets better. Again, my kids should be stopping school, so hopefully that will help with the bandwidth and things get better. But let's get started because it's 3 past noon. Welcome back, everyone, to your live 281 lecture. My name is Hector Garcia. Mentioned that last time, just in case you didn't recall. It's also there on the, I guess, slide. I also found that I had some real estate on my slide, so I added like a quote from Donald Knuth, who you might have heard of. If you haven't heard of, he's basically one of the grandfathers or grandparents of computing as we know it today. It's one of my favorite quotes. Is "Beware of bugs in the above code. I have only proved it correct, not tried it." Right. So he actually wrote this quote in one of his seminal books in computing. So it goes to say that sometimes, and you probably experienced this in Project One, you kind of assume that you have everything worked out in your head, and then you wrote the code that implemented everything that you had in your head, and then it doesn't work, right? Because in your head you proved that it was correct, but of course it's another thing when you actually have to go ahead and implement things. Bugs do creep in. All right, so today's lecture is on heaps and Heapsort. We'll also talk about priority queues, which, as we're going to see, priority queues is more of an abstract data type. If you haven't heard of that term before, we'll talk about it. Whereas heaps is an actual practical implementation thing that we will write code for, right? So we'll basically start discussing what heaps are, the concepts, then look at code for heaps, and then say how heaps correlate with priority queues. So basically, one potential implementation of a priority queue is using a heap, more specifically a binary heap, which is what we'll discuss today. For Project 2, you will be implementing several types of priority queues, or you'll have several implementations for a priority queue. One of them being binary heaps, which we're going to discuss in great detail today and give you code for, right? So make note for Project 2, you after this lecture, you'll basically have everything you need to go ahead and implement your binary heap in Project 2. Okay? It's also one of my favorite lectures to teach in 281 because this is likely the first time that you're run into kind of a non-trivial data structure, efficient data structure that you're going to be implementing, right? So up to now, you might have seen some very simple, well, not necessarily trivial, but simple data structures like a list and a binary tree. And today, this is going to be a full-on implementation of a I wouldn't say extremely complex data structure, but more intelligent data structure than the ones that you've probably seen before. Okay, so that's all right. Let's get on with it. In order to talk about heaps, we really have to talk about several concepts related to trees. Okay, so trees, you've seen either in 203, depending on where you took 203 and with whom. You also have seen some of it in 280 if you took 280. So a tree is a graph that consists. A tree is a graph. More generally, a graph consists of nodes, and there's edges connecting those nodes. And then more specifically, a tree is a type of graph. Okay. It is a connected graph without cycles, right? So that's particularly important, okay? And you can also say that same definition in a different way, which is it is a graph where any two nodes are connected via a unique shortest path, okay? Those two definitions are actually equivalent. I'll let you kind of rummage through your 203 material to check that out. It is a directed tree where we can identify children nodes and parent nodes. Okay, so an example of that is there on the slide, right? So A would be a parent node to its children B and C. Okay, and then in a binary tree, that is a node. A node has at most 2 children, right? So no more has either no children, 1 child, or 2 children. That's it. Those are the 3 possibilities for any node in a binary tree. Okay. And some additional terminology. You have the root of a tree, which is basically the topmost node in the tree. So in the example for that tree, on the slide, it would be A. But note that you do have subtrees inside of a tree because, as you're going to see, you can have a recursive definition. Trees are very amenable to recursive, just recursion in general. And so if we consider this subtree right here that I'm, whoa, 1 second. Then the root is going to be B, right? So this is the root of, call it subtree, well, I want to use a different letter. So subtree Z. Okay. Parent is the immediate predecessor of a node, right? So like I said, A would be the parent to C, C would be the parent to I, so on and so forth. Child is a node where the current node is a parent. Okay, so I is a child of C. B is a child of A, so on and so forth. An ancestor is a parent of a parent. Okay, so A is an ancestor of D, right? It's shown here, so this would be an ancestor to D down here. C, for example, would not be an ancestor to D. Then you have descendants with a child of a child. Okay. So then an internal node is a node that contains children. Okay, so as long as it has 1 child or 2 children, it's an internal node. So technically, the root node is considered an internal node. Then a leaf node is a node without any children, right? So you'll find the leaves at the bottom of the tree, right? So let's see if I can switch colors with my nifty pen, right? All these down here are the leaf nodes of the tree. All right, so that's mostly review. And what you've likely seen before is an implementation of a binary tree using a binary tree node struct or class. Okay, and so you've probably seen before this kind of class declaration that's on the slide, where you have using pointers, right? So you have a pointer to the left child, you have a pointer to the right child, and then you have some internal value to the node that is maintained, right? So this is actually using some generic, so we assume there's some other class called item, okay, that we're using to declare the item that belongs to the node in line 5, right? That's the declaration. So that would be like a data or a key. You could have an additional declaration and separate the data from the key, okay? But especially for this lecture, we're going to always conflate the key and the actual data that we're trying to hold, right? So we're basically just going to be using integers, and the integers that we're looking at are both going to be the key and the data. But that, in a more generalized implementation, need not be so, right? You can have some key that we're going to look at to organize or structure the nodes, and then the data, which is just whatever the node is meant to contain. Okay. All right. So as I mentioned, trees are by definition recursive structures, so very amenable to just recursion in general and recursive algorithms. And that is because, given any tree, you can go ahead and look at a subtree within that tree, right? Any of the properties that we can describe for trees can be defined using recursion. So for example, you have the height, okay? And because this is recursion, there's going to be the base case, and then there's going to be the recursive calls. So if you have a property that's height, okay, which is, how high the tree is from the base of the tree to the root, the base case is that height at empty is going to be 0, right? So it means like your tree is empty, it has a height 0, right? So that means that as soon as the tree has at least one node, right, it's going to have a height of at least 1, right? And the recursive definition is height at any node is going to be the max of the height from the left child, between the height of the left child and the height of the right child plus 1, right? So this plus 1 is always going to account for that root. Okay. So for example, here the height of B would be 3. Okay? That is because it'll be the 1 here accounting for B, plus 1 plus 1. Makes sense? That's height, so fairly simple. Then you have size. Size is, again, size of an empty tree is going to be 0. But then size at any node is going to be the size of the left child plus, right? So not a max, it's a plus, size of the right child plus 1. So that's fairly easy. I'll let you just work it out. And then depth of the tree is how far to the null pointer by looking up, right? It's the inverse of the height, right? So height is kind of looking top to bottom, and then depth is looking bottom to top. Okay, so the depth of B is going to be 2, right? Because it's going to be the plus 1 right here that counts B, and then it will be the depth of the parent, which is A, and that's going to be 1. So it's 1 plus 1 gives you 2, right? So that's our quick examples. Those are fairly easy. I highly encourage you to implement, like if you haven't done it before, okay? Fairly easy to just copy paste the code that we give you on this slide, okay? Create a very simple tree and then implement these functions, right? It's good practice for something like a lab or an exam. Okay, I think we do have a lab where we have you implement some of those things, but just in case, you can also do it on your own. All right, so that's basically a review of trees. Which again, you've probably seen before, but if not, it's not terribly complicated. But we are going to use a lot of those terms, so get familiar with them when we talk about heaps. All right, so I'll pause here to see if there are any questions, just to see, do I have anyone from staff on the chat? Okay, so I have streaming. Is the volume low for y'all? Oh, not for me. It might be the YouTube player volume. Fine for me. Okay, so good. The volume is good. For an integer key, any number. For a string, maybe a name or something. Yeah, those. So I think Ian posted an example of, like, if you wanted in your tree struct or tree node struct to separate the data from a key. So maybe the key, which is something easy to compare, that could be an integer, and then the data could be something more complicated like a string. But again, for the rest of this lecture, we're going to assume that the key and the data are the same thing. We're basically just storing an integer, and we're going to use it as the key as well. Okay. For the tree project, for the project in 280, the key was the word from the Piazza post with the value. There you go. What's the difference between a key and a datum then? hopefully I don't Agam. Hopefully I don't butcher the name. I apologize if I do. There is in this lecture we won't see a difference because we're conflating the two. Okay, just to keep things simple and write less code, as you're going to see. But in general, you would want to separate the key from the datum. Okay. Maps aren't trees. A map has two keys in the data. So yeah, a map is not a graph data structure. Definitely not a tree. Oh, well, if you're talking about what's implemented behind the scenes, let's put off that conversation. How an STL map, for example, is implemented behind the scenes. A little confused on the difference between height and depth. Yes. So height, look at it. Let's go back to the example. Okay. Height is just for any particular node. Let me erase some of this. Height, if we're talking about B right here, height is basically measuring this distance, okay? And depth is measuring this distance right here. Does that make sense now? Monish? Give it a second. I know there's lag in between what I say and what folks, but hopefully, so let me write it here. So this would be height. And this is depth of B, by the way, of node B. So it's not of the total. So just to partially correct, Seb. I would correct the fact that you're mentioning total height of a tree. You can measure the height of a node inside of the tree, like for the B example that I just went over, right? But if you measure or compute the height of the root node, which in this case is A, then that will give you the total height of the tree. Okay. All right. So heap fundamentals. So and this is going to be a bit jarring, because even though we've kind of described the tree node class, and we kind of went over it, and the pointers to left child and right child and all that stuff, now we're going to tell you to kind of forget it, okay? Because the way that we're going to implement trees is not going to be with a class like that, okay? So bear with me. We're going to talk about it in a second. Okay? What we're going to do is implement such trees using an array. And you might be like, wait, what do you mean an array? Well, how would we use an array? Okay, so again, bear with me. But in order to be able to use an array to represent a binary tree like this, we're going to add some particular properties for the trees that we're going to consider, right? So they are binary trees, but we're also going to consider that they are complete binary trees. Okay, so this is a restriction that we're going to add. The trees that we're going to be interested in are binary trees, and they're also complete binary trees. So completeness means that the way that you fill up the tree is in a specific order. Okay, so if you recall, if you've seen binary search trees before, you don't. There is a constraint that you need to meet, but it's not related to how the nodes are inserted in the tree in terms of order, right? Here we're going to say that if we're going to insert a node into the tree, it's going to follow specific order, and it's going to be top to bottom, left to right. Okay. So the way that you fill up every node in the tree is in level order. Okay. If you recall what level order traversal is, if we started, say, from an empty tree, the order of insertion of these nodes are going to follow the alphanumeric ordering of the keys, which in this case are A, B, C, D, right? So this is the order. So this would assume that A was inserted first, followed by B, followed by C, so on and so forth. And that's level, right? And that would be a level order for the tree. So for example, the tree in the middle is not a complete tree because it doesn't satisfy that property, right? So we have A, B, C, D, E, F, G should be here, right? But instead, right, these are reversed. Notice that the tree in the middle is something that you could get in a binary search tree because if you recall, the condition for a binary search tree is just like which side should I insert the node depending on the comparison to the key of the current node. And so similarly, this is not a complete tree, complete binary tree, because the insertion order would have been A, B, C, D, E. Oh, I see an I. That shouldn't be there because the next node that I would see should be an F, right? Which is here. So this is bad. It's also bad because G, for example, should be here, yeah, instead of here. So that's not a complete tree. Those are binary trees, but they're not complete binary trees. Okay. And we're adding that constraint because that constraint is going to facilitate our representation of a tree using an array. Okay. So, all right, yes, so we have someone from staff on the chat. Great, thank you. Don't know who it is, but thank you. Helps a lot. Let's see, does that matter if a node is going to have two children? Doesn't that rule out the possibility that a leaf node would be to the right? So I'm going to put off that question because I don't quite understand the question, so I'll come back to it. Okay, and then hopefully we'll get an answer. Let me go next to representing a complete binary tree using an array. Okay, and this is what it would look like. Okay, so you have the same tree that we had before. It's on the left there on the slide, and then you have the array representation of the same tree. Okay, so notice that we basically have the nodes in the tree sorted left to right, okay, in the array. So A goes here, B, C, D, so on and so forth, right, all the way to the end. So it's labeled right there. The number that sits below the drawing of the node is signifying the index that we would use to fetch that node from the array. Notice that we've started our indexing at 1 rather than 0, okay, in the array. That has a purpose. It's actually going to make some math that we're going to look at next much easier. Well, not much easier, but just nicer, okay? And you would say, well, what happens to the 0th node in the array, or 0th element in the array, 0th slot in the array, whatever you want to call it, right here, where that is supposed to be open and closing square brackets, we're just basically just going to ignore it. Okay, so let's just do that to signify that we're ignoring that. You say, well, isn't that wasteful? Really, it's just one slot out of an array that could be, sized in the thousands and thousands. So it really not going to make a difference performance-wise if you just ignore a single element in the array. Okay. Cool. All right. So let's look at why we would want to index the array at 1. And by the way, in Project 2, when you implement it, you're welcome to use either this 1-based indexing that we use here in the lecture, or if you want to just redo the whole thing using 0-based indexing, meaning from the very first, you don't waste that first element in the array, you're welcome to do it. Okay, it's just basically going to be working out the math that you're going to see next. Okay, so this math, remember, is going to be for the one-base indexing of the array. For any node, okay, given the current ordering that I have in this array for the nodes of the tree, that means that if I pick any index I can reach the parent by just doing I divided by 2, and this is assuming integer division. That's all I need to do. Okay? And if you don't believe me, go back to this example and say, like, all right, I don't know, I want to find the parent to E right here. All right, we'll find E in the array right here, and then you have 5 divided by 2. Okay? That gives me 2 integer, and lo and behold, right, 1 and 2, it tells me in the array that it's B, and yes, true enough, B is the parent. Yeah? Makes sense? All right, so additionally, if I were to do from any node, trying to find that node's left child, all I have to do, conversely, is I times 2. Again, if you don't believe me, pick any node in the tree and say C. Okay, I want to find the left child of C. Okay, let me pick a different color for my pen. Let's say I want to find the left child of C. Well, that would mean C is indexed at 3, so I do 3 times 2. That gives me 6. So I jumped to 6, and lo and behold, it tells me that it's I in the array. Sure enough, there it is, I. Okay, and then, all right, so how do I find the right child? Well, it's actually fairly simple still. I would do I times 2 plus 1. Again, you don't believe me? Check the example. Then the question is, and I'll leave it to you all, give you 1 minute, see if you can figure it out. How do I determine whether a node is a leaf node? Okay, it's a fairly simple check. See if you can figure it out by inspection. And all of this, you know, I'm sure if I gave you this example and I told you, like, work out how I can compute the left child and the right, you would just spend, I don't know, half an hour, 1 hour, and, you know, just by trial and error would figure out what the math is. But we're just, you know, giving it to you because it's easier that way. And again, if you were intent on, oh, everything's buffering. Things are buffering. Okay. Let me know when we're back, and then can someone post where it might have buffered a bit. I don't know if it just. Why is it buffering again? I don't know what's going on today. Okay, so we're back now. And I have Richard who, okay, so I guess everyone heard my question, or at least Richard did, which was, how would I determine if a node is a leaf node? And that would be if I just check whether I is greater than however many nodes I have divided by 2. Okay, so just make some space there. So whether that index represents a leaf node, you would check by doing I is greater than whatever the size is divided by 2. Okay, so the size here is 1, 2. Notice that this is size in how many nodes are in the tree, right? So how many non-empty slots or elements I have in my array, not the capacity of the array, right? That's going to be important for project 2. Oftentimes we see that you know, people use the vector, which I believe we call data, and we do data.size, and that's what you use. And no, don't use that. What you want to use is whatever the number of elements, which is usually an integer you keep track of internally in your heap. Okay, so it'll be whatever the size is divided by 2, and the size here I believe is what, 1, 2, 3. Oh, it's 9. So 9 divided by 2, and so if the index of the node is greater than half of the size, then you know it's a leaf node. Fairly easy. Okay. Notice that all of this, if we were using a tree node data structure, like the pointer base one, it would require traversals in the tree, which is, much less efficient than just doing random access on an array, right? So that's one of the nice benefits of a binary heap implementation using an array, or a vector for that matter. If I haven't mentioned this before, I use the terms vector and array interchangeably, okay? Because they basically are interchangeable data structures. Cool. All right, so reiterating, this is for when we're doing the whole bit about just ignoring the very first element of the array, okay? If you do that, all this math would work out. It's going to work out, and I'll leave you as an exercise to come up with this math that would correspond to actually not wasting that very first element of the array. Cool. All right, so that array is what we're going to use to store our complete binary tree. Okay. And what we're going to use is complete binary trees to implement a heap. Okay. So in addition to having the property of being a binary tree, of being a complete binary tree, we're going to add a third property, which is known as a heap ordering property. And then we're going to have a full description for a heap implementation. Okay. Now heaps come in two flavors, max and min heap. Okay. For the rest of the lecture, we're going to assume that it's a max heap. The difference is going to be apparent once I describe what the heap property is. So let's assume that we're going for a max heap. That would mean that for any node in the tree, any of its children, okay, and descendants are going to be less than the current node. Okay, and notice that this is very different from the constraint that I have for a binary search tree, right? Remember, a binary search tree constraint will say like all the nodes on the right subtree are going to be greater than the current node. Well, it depends which way you decide to go, but let's assume every node in the right subtree is going to be greater than the current node, and all the nodes in the left subtree are going to be less than the current node. The heap property is every node, be it on the left subtree or the right subtree, is going to be less than the current node. And it's less than assuming that it's a max heap. Okay? And then if it were a min heap, then the constraint reverses, right? It would be every node that sits below the current node would have to be greater than the current node. Okay? And notice that if the current node happens to be the root of the tree, that would mean, by definition, that the root will contain the most extreme value for the key in the tree. Okay? So in case of the max heap, the root is by definition going to be the maximum element in the entire tree. Okay? Make sense? I'll stop there to see, look at some questions here. Sahil, if either child index references a null pointer, so this is an array, so there should not be any null pointers, if that makes sense, or if both actually. Again, so what would happen in an array implementation is you can try and query a left or a right child for a particular node, right? But you'd want to check whether that query would put you, right, if the math that you worked out to check the left child puts you beyond the number of elements in the array, or again, the size, not of the array, of the number of elements in the array, then you'd know that no such left child exists, for example. Okay, can we check whether or not the node has a left or a right child? Yeah, John, that's what I was just describing. You can check by just checking against the size, right? If you're computing the left child and that value that you come up with is greater than the size, then you know that child doesn't exist. Okay. Okay, I think we're good. Is it complete heap ordered binary tree recursively, or can heaps be other trees too? No, heaps cannot be any other. It has to be a complete binary tree that follows the heap order property. Otherwise, your heap will not work. There's other types of implementations for a priority queue other than a binary heap, right? In fact, your priority queue is going to implement pairing heaps, which are conceptually very different from binary heaps. Okay, they achieve the same purpose, which is to have a fast access to the most extreme element in the container. Okay, but they do it by very different means. Primarily, binary heaps are much easier to implement than pairing heaps, as you're going to see for project 2. Okay. All right, so let's get going in the interest of time. So we went over the heap ordering property, right? So a heap has these two crucial properties that I just talked about. In fact, in response to a question on the chat, completeness, again, complete binary tree, and follows the heap order. Okay, so we leverage these two to have not only an efficient data structure, but an efficient implementation of that data structure that uses an array rather than a pointer-based class or struct for the nodes in the tree. All right, so this is where we put it all together, specifically with regards to what we mean by a priority queue. So a priority queue is an abstract data type, also known just by ADT, right? So if you might have heard of the term ADT, that stands for abstract data type, which is also known as an interface, right? So usually priority queues is what we call the interface for a bunch of operations that we'd like to see in a container, okay? And so for a priority queue, one of the like to see is fast access, specifically constant time access, to the most extreme element in the container, okay? And it just so happens that a binary heap is an implementation that facilitates that same want to have in a priority queue. So that's why a binary heap satisfies an implementation for a priority queue abstract data type. Okay. Now, that's not to say that you could write a tree implementation of a binary heap. You could. There's nothing preventing you, but it's going to be much, much less efficient than if you use an array implementation for your heap, right? So this can be confusing, but I guess that's how it works. We use arrays or trees to implement a heap, but then we also say that we use a heap to implement a priority queue. right? So the arrows in these box figures that we have here imply a direction of implementation, right? So we use arrays or trees to implement a heap, and then we use heaps to implement a priority queue. And also, we're going to use heaps later on this lecture to implement the Heapsort algorithm. Okay. All right. So let us get on with heap fundamentals. So now that we know how to represent heaps, we now have to discuss the operations that we're going to need to actually make a heap work. Okay? Because we haven't really spoken about, like, oh, what happens if I take one of the nodes in the heap and I take it off? Like, what's going to happen, right? What happens if I take the top, the root node, if I take it out of the tree, what do I do? Okay. Conversely, how do I add a node to my heap? So that's what we're going to talk about right now. But what we're going to discuss first, okay, they're kind of, you'll see how they're specifically related, is if I take a tree and I break the heap ordering property, how do I fix it? Okay, so we're going to come up with these functions to fix a heap, and those are the same functions that we're going to use to actually implement functions for inserting or removing from a heap. Okay. All right. So let's say that I wanted to modify a heap. Let's say I have that current heap right there. Again, we're always assuming it's a max heap. So let's say that we wanted to increase the priority. Okay. And recall that we're conflating the key, which would actually use to compare the nodes, with the data itself. Okay. We're just using integers in both, so we might as well use the same integer. But just to remind you, this need not be so, right? So you might have key, which will signify priority, and then the data is just something that we manipulate along with the key throughout. Okay. So if I wanted to increase key, meaning if I take, say, in this example, we're going to take 8. Okay. So if I look in my, assuming that this array is called heap, so this is called heap. So heap at 8, which would mean this right here, element in the array, its current key is 2. And I'm going to increase it to 35. Okay, that's how I'm modifying my heap. If I do that, I will potentially break the heap property. Okay, so let's see what would happen. And usually I write this with my pen, but I believe we have some very cool animations. Do we? Ah, there it is. Okay, so let's go over our new and improved animations here. So let's say that we increase key at heap 8 from 2 to 35. Oops. That means in the tree picture, hopefully you didn't miss the animation, but just in case. So you see we had 2 there, right? So this is node 8 right here. So what we're going to do is change that to 35. Okay. If we do that, you clearly see that we have broken the heap property. Okay. Because we have 9 here, which is less than 35. Can't have that. Okay. All right. Well, how do we fix it? Well, it turns out to be fairly easy to do. What we can do is basically bubble up the value as much as we can in order to fix the overall heap property of the tree. So what we would do is compare 35 against 9, determine that it is larger than 9, and swap. And do that recursively. So now I would compare 35 against 18, determine that there is still a breakage there, and so swap. Okay, nifty animations. Okay, now I would compare 35 against 81 and say like, well, oh, this is good. This still holds for the heap property, so no need to swap, and I would be done. That's all the swapping that I would need to do. In the array, which is now the animation that's shown at the bottom of the slide, I would take the 2, make it a 35. That's the update that I'm doing. Yeah. And then just as before, I would compare against the parent, which would be 9. Again, I would do that by doing I, which in this case would be 8, divided by 2. Gives me 4. So that's how I can easily compare against the parent. Determine that I need to swap, so I do. Okay, rinse, repeat. Okay, 4 divided by 2 gives me 2, so I compare against 18, make that swap, and then 2 divided by 2 gives me 1, so I would compare against 81, but determine that there's no need for swap. Okay, so fairly straightforward process, and this is known as a fix-up. Okay, operation. Okay, because what we're doing, if you see, in the previous animation, is that we're at the bottom and work our way up, fixing the tree. Now you could write a recursive implementation for this, but why would you? It is way easier and much straightforward and easier to test if it's just a while loop. Okay. So in this while loop, notice that all we're doing is while, so this is line 2 here on the slide, while basically I have not gone out of bounds, because remember, the left bound in the array in terms of elements is whatever sits in the element index at 1, right? We're ignoring the 0th element. So while I haven't gone beyond the left bound of the array, and I can swap, which is that condition where I'm checking the parent, right? So this is basically parent, the k divided by 2. While I can swap, I swap. And then I basically move to the parent, which is line 4. And all I need to do to move to the parent is take the current index, which is k, divide equals by 2. Okay? So fairly simple or straightforward procedure here. Okay? And I ask you, and I'll take 30 seconds or a minute, see if I see some responses in the chat. What is the runtime of this function? And maybe there's also lag. Anyone? Bueller? What is the runtime of this function? I have an answer. Log n. Yes, indeed. Okay. Oh, how is it log n? It's a while loop. Well, it's a while loop, but you see that the stoppage of the while loop is going to be driven by k, right? And k, I'm decrementing by doing divided by, right? It's not really a decrement, but the jump in k is a factor of 2. Okay, so that's what gives you log n time. Again, log n being the number of elements in your heap, not the size of the underlying array, right? At any point, you can have the size of the underlying array be much bigger than n, which is the number of elements in your heap, right? So always make note of that. Remember it when you're implementing stuff in project 2. All right, so we have a function to fix things when the key is increased, but of course, you can also modify a tree by taking one of the nodes and changing the key by. So let's look at that case. So let's say that I want to reduce a key. So I'm looking at, so this is heap as an array, okay? And I'm looking at 2 right here. So that's the index. And I say, well, its current value is 18. I'm going to decrease it to 3. Okay? Let's see what happens then in our nifty animations. So we have a change from 18 to 3. And now you see that it's kind of the very similar situation, except, you know, whereas for increasing the key, in that situation, we just needed to look at the parent to see where to swap. It is a little bit more complex when we decrease the key, because we could pick between the left or the right child. Okay? So that's the only thing that makes it a little bit more complicated, but it's, you know, overall it's kind of the same approach, right? Given a change in the current node, I want to walk down my tree whilst fixing whatever is wrong. Okay, it's basically the same approach. Earlier we were walking our tree up from the node that we changed. In this case, we have to walk our tree down, but as we walk down, we could either go left or right, so we have to pick which way to go. And the way that we pick is whatever child node has the larger key. Okay? Video's choppy again. So I'll take 1 minute, see if it gets better. But then there's the lag. But hopefully it gets better soon. I apologize. I do not know what's up. Maybe my kids, one of my kids is using some nifty thing for their schooling. I have to figure it out. All right. All right. So let's continue. So just get our bearings again. We had 18 there. If you know, in terms of the tree, that's what we're looking at. We changed it to a 3. So now we need to pick as we walk down to fix the heap property, because recall, if that is a 3, then that is smaller than either 9 or 7, and we can't have that, right? Well, you know, what we need is the larger number should be at the current node now. So how do we determine that? Well, we compare against the 9 and the 7 and determine that 9 is larger. So that's what I picked to swap with. Boom. Okay, and then this is basically a recursive function, although again, we're obviously not going to implement it as a recursive function, but conceptually, it's easier to think of it recursively, because what we would do is then move to that node and rinse repeat, right? Compare against its children and compare 3 against 2 and 4, determine that 4 is larger, so that's the node that I would pick to swap with. Okay? And boom. Then I'd be done because I'm at a leaf node. Okay, so in the array, the way that it would look in the array is this lot right here is where I make my change. So turn the 18 to a 3. Then compare against 9 and 7. Again, using my nice I times 2 for left. And I times 2 plus 1 for right. And I apologize for my terrible handwriting, but it's hard to write out with this pen. And so that I compare against 9 and determine that that's swappable, so I do. And then rinse repeat, right? Now I compare the 3 that now sits at node 4 and compare against 4 and 2 and determine that 4 is larger, so I make that swap, right? So it's just basically the same thing that we saw in the tree picture, but now in the array. Okay. All right, so let's look at an implementation for this function, and it's called fix down, because if the other function was fix up, and again, what we were doing was traversing up, then this one should be called fix down, because it's exactly what we're doing. We're traversing down the tree. Okay, so you can see how there's similarities, except it's kind of one is the opposite of the other, right? So earlier we had divided by 2 when we were moving up the tree, but now we're going to have times 2, right? And in fact, this is saying, well, while I have not hit the right bound of the array, again, determined by heap size, not the size of the underlying array, so not data.size. I basically check the left child, okay? And if the left child is smaller than the right child, right? So this is basically left, and of course, j plus 1 would be right. And this if on line 4 is just figuring out which child to swap with, right? So if you determine that the right child is the one to use, then all you need to do is take j and do a plus plus, right? Because remember, the difference between the left and right child is a plus 1 in terms of indexing. Given the math that we've been looking at. All right, if I'm looking at the largest one of the two, right, which is now j, and I determine that the current node that I'm looking at is indeed larger or equal for that matter, then no breakage. So I'm done. I would break, right? And I would strongly discourage the usage of break inside a while loop, but it's easier to read this time around. But the programming gods will come crashing upon you if you use a break inside a while loop. Anyway, but here it's okay. No worries. And of course, in projects, we don't really grade that stuff, so you're free to use whatever you want to use. So otherwise, it means that there is a breakage, and what I would do is in line 6, I would do the actual swap. And then moving down is just, hey, whatever I determine I did the swap with, I'm just going to assign a k. It comes back, rinse, repeat. Okay, and that's your fix down function. Okay, which implements basically the example that we saw earlier in the slides. With the sample tree. Cool? All right, so now that we have fix up and fix down, meaning we have the means to fix a broken heap property, now you'll see that it's incredibly easy to implement like a push and a remove from my heap. Okay? Buffering again. I'll pause. Oh, man. In the meantime, why not use a break in a while loop? It makes things harder to read in terms of code, right? So if it's a while loop like the one that we have in the slide, it's fairly easy to read. That's fine. But remember, sometimes you're going to have while loops that are like fairly big, that if you break in some middle of the loop, it kind of is jarring. Like if you're trying to understand what's happening in the loop, and it's you kind of see a break. It's like, oh, okay, so now I break out of my loop, and I gotta go back and remember what was happening at that point to determine the breakage. So, if in general in programming using break or continue are kind of frowned upon. I mean, but to each his own. And my developers in my team, if they use a break, I tell them like, you need to structure your code to make it more readable, because you should avoid the usage of a break inside of a while loop or a for loop. Okay, Of course, sometimes maybe there's a particular situation where you can't help it, but I can't think of any. Usually you can refactor, you can restructure things. All right, so now that we have our functions to fix our heap, we can implement push and remove functions, or push and pop, however you want to call them, for a heap, which would mean that having those functions will give us everything that we would need to implement a priority queue using such a heap, right? So priority queue, it's abstract data type, what it wants. Remember, this is basically just a description of a wish list for our container. And so that wish list or interface is that we want insertion, which is push, inspection, which is top, okay, which is just checking, fast check of that maximum element or most extreme, right, to accommodate the cases where you have min heaps, most extreme element in the container, and then removal, which is pop. Okay, you will see priority queues in project 2. You will be tired of them by the end of project 2. You will also use priority queues potentially for other algorithms that we'll discuss later on in the semester. Okay, so that's why we talk about them so much. All right, so let's say that we're talking about a priority queue and we want to insert, and this is a priority queue that we're implementing using a binary heap. Okay, so let's say that we have PQ and we're doing push 100. The way that this would work is as follows. We would add what we're looking to push, the element that we're looking to push, or the key that we're looking to push, as the last element in the array. Okay. Well, in the animation right now, it's using the tree, so it would be the last node in the tree. And remember, it's a complete binary tree, so the way that we would add that node is top to bottom, left to right. In other words, level order. So it would go as a left child of 7. Okay. All right. So we place 100 right there. And then what we would do is fix up, right? So we inserted there and fix up. And so 100 would be compared against 7, determine that 100 is bigger. So swap, right? Same thing that we did for fix up. Then do the same thing between 100 and 18, fix up. We'll continue and compare 181, which will be our final swap, because now we're at the left bound of the array, right? Or the root of the tree. So you see that I basically was able to explain away push by just saying, oh, I fix up. Yeah? So we're going to look at a code for the push function, and it's basically going to be 2 lines of code. One of them is just calling the push function. Sorry, not the push function. One of them calling the fix up function. Okay, so this is what it would look. Oh, this is what it would look like in the array, right? So it's not that we would, well, assuming that our array is at capacity, we would have to create a larger array to fit the new element. But hopefully we're at a point where we haven't run out of capacity. So putting the new element at the end of the array, or at the end of the pre-filled part of the array, it's a real easy operation. So we just place it there, 100, and basically compare against 7, do the swap, compare against 18, do the swap, compare against 81, do the swap, right? That's what it would look like in the array. It's fairly nicer to look at in the tree than in the array, okay? But it's useful to see both, just so you can get your bearings as to what happens in the array given the tree. Okay. All right. So that basically covers insertion or push into a priority queue. Okay. So as I told you, as I mentioned, it's basically 2 lines of code. It's just, place the element right end of the array, okay, which is, heap size. Then increment heap size by 1, because remember, after line 2, it would mean that now the number of elements in your heap would go up by 1. And remember, if the plus plus operator is to the left of, excuse me, is to the left of a variable, it means that that incrementing is going to happen before the execution of the rest of the stuff that happens at that same line, right? So basically, we will increment heap size first and then place that element, the new item element there, okay? And then again, I don't know if I mentioned this before, but these function implementations assume that there is some item class somewhere defined that we're using to represent an element inside of the array for our heap. And then all we do is call fix up given the heap array. So this is just the heap array that sits behind the scenes, and heap size, which is where heap size, not hip size, heap size, which is where the new element sits, right? And then fix up will just take care of the rest. Okay, so fairly straightforward. Now deletion, all right, otherwise known as pop. Okay, so if I wanted to pop my priority queue, how would I do that? Okay, well, the way a priority queue goes, what you're popping is always going to be the max or most extreme element in the priority queue. So that would mean, it says no data. Hopefully we can come back. All right, I'm giving it a minute. See if it comes back. Okay, I think we should be back. You should have seen some buffering according to my stuff here, my tech here, but I think we're back in business. Or maybe not. This was not happening last Tuesday. I think I'll need to get in touch with Xfinity. All right. Someone in the chat tell me the status of the buffering, just to determine whether I should keep going. I think they're drawing the tree just for Visual 6, but the implementation is using it. Yes, William, that is correct. All of this, please note, the actual implementation that we care about is the array implementation. We still represent the tree because, you know, it's easier to conceptualize as a tree than as an array. But behind the scenes, it's all an array. You'll never, in Project 2, for the binary heap, you will not be using a tree node class or anything like that. All right, let me keep going. I think hopefully we're back in business. It says that viewers are buffering. I'm going to keep going. So we have deletion or pop. How do we do that? As I mentioned, you would want to just remove the most extreme element. Oh, man. All right. Give me 1 minute. I'm going to see if I can find something that might, not quite sure, because I should be in class. So I'll be back in a minute. All right, I'm back. I can't find anything that's different from last Tuesday. So I think our tech issues are more of Xfinity, which is what I use. Sadly, that's what I have to use for my interwebs. Monish, can you go over the difference between heap size and array size? Yes, I can. Let's say I'm going to use this drawing right here. If this was an actual array that you were writing in code, right? Well, first it would have like some slot right here for the first element, that 0th element that we don't care about. Okay, but then behind the scenes you might have another part of the array, a bunch of slots that are unfilled, right? They don't contain any elements. So this right here is an internal variable that you will keep, that you may call heap size. So its value right there would be 9. Yeah. Whereas the array size would be out here. Okay, so that's the difference. Does that make sense, Monish? And I hope I'm pronouncing your name correct as well. Yeah, Xfinity sucks. So yeah, array size is really the capacity of the array, whereas heap size is how many elements you really currently care about in the array. All right. So let me, just so we can get back to deletion here. All right, because we have 15 more minutes and we still have Heapsort to cover. Okay, but that's okay. If we don't get to it today, we can continue Tuesday. I think with this deletion, we would cover most everything that you need to know for project 2. Okay. All right. So back to deletion again. It's a matter of using, instead of your fix up, using your fix down function. Okay. So when we delete, when we pop, what we're looking to remove is basically the root, okay, which is the most extreme element, okay? And what we would do right there is take that most extreme element, remove it, okay, and take whatever is the last element in the array, okay, and place it as the root element, okay? So we swap the 4 that sits here at the end of the array and swap it with the root, or right over. Okay? So we just move it there. So you can see how this is kind of working things, but the other way around, right? When we insert it, we place the new element at the very end of the array and then fixed up. When we're deleting, what we're doing is moving the last element to the front of the array, and then what we're going to do is fix down. So it'll be comparing 4 against 18 and 14 and determine that 18 is larger, so that's what I would swap with. Then take 4 and determine that I would swap it with 9, and then I would be done. Okay? Because at that point, I can just forget about this slot in the array that is represented by this empty node in the tree when we do heap size minus minus, right? Because now our heap has gone down by one element. So that's represented by the removal of that node. Oops, excuse me, of that node right there. All right, so let's look at what happens in the array itself. Basically, what we would do is, well, this is the animation is representing us as kind of taking out the what is it, 18? Sorry, sorry, the 81. But really, if we just basically take the 4 and write over the 81, it's just the same effect, right? Right. So take the 4, place it at the first element, and then do our fix down. Okay. So on and so forth. All right, so again, our deletion pop is just 2 lines of code, right? So it is placing of line 2 is placing of the last element as the first element in the array. Remember, first here means index at 1, okay? And then fix down right here. Okay, which we can just pass it as 1 because that's where we placed the new element. Okay, remember, if you go back to the fix down function declaration, the third parameter is the index of where the current element is at. Okay, in this case, the current element is going to be the root, so it's just 1. All right, so we basically have everything we need to implement a priority queue using a binary heap, and I'll let you look at that XKCD. Somewhat funny. So just to summarize what we mean by a priority queue, as I mentioned, a priority queue is an abstract data type, or ADT. It supports primarily insertion, looking at the most extreme item in the tree, in the binary heap tree. We use top for that, and then it also supports removal. Okay. Now, in fact, there are multiple ways that you can implement a priority queue, as I mentioned earlier. The one that we're discussing today is the binary heap implementation. For project 2, you're going to implement an unordered array priority queue. So basically, you're going to implement the insertion, removal, and top operations using a vector behind the scenes, or an array. No names, terms used interchangeably. But it's going to be a plain old vector. There's no particular ordering, right? So in those under those constraints, how would you find top? How would you insert? And how would you remove? Well, for inserting, that's fairly easy because we don't care about ordering, right? So we just place the element in the first slot that we have available, right? Now, top becomes linear time because there's no particular order in the array, so therefore, on the worst case, I have to search all the elements in the array to find my most extreme element, right? Basically, it's a max function, like that finds the max or min, depending on whether it's a min priority queue or a max priority queue. Has to search the entire array to find it. And then removal is depending on what happens, okay? Because there's no specific order, you will have to, depending on where the element that you're removing sits, right? So if it's at the end of the array, that's constant time. But if it's in the middle, you're going to have to move things around, okay? So that can be linear time. And then in a sorted array, right? So it is an array where we're always maintaining the elements in sorted order. You have insertion that takes linear time, right? Compare that to constant time with an unordered array, right? Insertion now takes longer because since we want to maintain the sorted elements invariant, then we need to find the right place where you're going to insert this new item or element. So that takes linear time because we would have to find where to place it. And if it's sorted, you would say like, well, I can use binary search. Yes, very good. So that gives you log n time. But once you insert, you're going to have to shift everything in the array. So that still takes linear time, even though finding where to place it might take log n time. When you insert, is still overall going to take linear time because of the shifting of the rest of the elements when you insert in the middle of the array. But because it's sorted, then it's constant time to find the most extreme element, because it's going to be the first element, depending on whether you're sorting increasing or decreasing. And then removal is also fairly easy because it's just going to be the most extreme element that always sits at the end of the array. So you can just you don't necessarily have to shift everything. You just have to remove the single element. Now in a heap, everything for the most part is more efficient. It's log n for insertion, as we saw, because of the fix-up function. It's also log n for removal using fix down. Inspection is just constant time, because all we need to do is look at the root of the tree, which is again the first element in an array. The caveat is that it's a little bit more complex to implement, because you need to write code to maintain the heap property, which are the fix up and fix down functions. Okay. Cool. All right. So let's look at some interesting functions for a heap, binary heap more specifically. The first one is heapify, and then we'll talk about Heapsort. So we'll finish today, because I'm running out of time. With heapify. Excuse me. My accent is getting the better of me. Heapify, and then Heapsort we'll do on Tuesday, which works out well, because next week is when we start discussing sorting algorithms in general. Okay, so heapify, otherwise known as building a heap. What we're doing there is taking a random array. How do you take a random array of integers, for example? Because all that we've been doing all along is dealing with integers, and move things around in the most efficient way, such that the output is an array that satisfies all the constraints for a heap, meaning it will represent a complete binary tree where all the elements satisfy the heap order property. Okay. Now, you could say, well, how about if I just, take every element in my random array and then just declare an empty heap and then just use the push function n times. Totally doable. The problem is you run into a runtime of n log n, right? Because remember, the push operation takes log n time, and you're going to do it for every element in the random array, so that's n log n. And then the worst, even worse, is the fact that you have to use O of n extra memory, because you'll need, when you declare the separate heap, you're going to be declaring behind the scenes a separate array that you're going to use to hold everything that you're going to push, right? So it's O of n extra memory. Okay. You can also say, well, it's not hard to see that an array that is in sorted order is going to satisfy the heap property. Okay, I'll let you figure that out. You can show that by induction. Like you can prove it by induction. But if you take an array and you sort it, it's actually going to be an array that does represent some complete binary tree that follows the heap order property, right? So you can do that. You can say like, all right, I take my array, throw it to a sort function, and then that's it. I'm done. All right, so that's better. It's not using extra space, right? Because sorting algorithms, as we're going to see in later lectures, you can do in place, meaning in the same array that you're given as input, you just shift things around so that it comes out in sorted order. But the runtime is still n log n. Okay. And what we're going to show you is a procedure that actually achieves the same thing in linear time instead of n log n time, which is what you would need for either sorting in reverse order or doing n pushes into a new container. Okay. What we're going to do is modify the given array and basically use either our fix down function or a fix out function to fix it so that it represents a complete binary tree that follows the heap order property. Okay. Now there's 4 possibilities here, right? Because I could iterate my random array left to right, okay? Which, if you think of the tree pictures that we've had, is like traversing the tree top to bottom, okay? Remember, the very first element is actually the root, right? So if you're traversing the array left to right, you're basically going, again, as far as the tree goes, top to bottom. So you go either top to bottom, doing fix ups or fix downs, or you go bottom up, which would be traversing the array from right to left, doing fix ups or fix downs, right? So there's 4 possibilities here, right? I go top down, doing fix up, or top down, doing fix down, or I do bottom up, doing fix up, or bottom up, doing fix down. So there's 4 possibilities to go about this. 2 of them don't work, and 2 of them do work. Okay. So if you proceed bottom to top, right? So that is, again, would be traversing your array right to left. Okay. Doing repeated fix down. That is the best and ideal way to do it. Okay, this is what we're going to go over. You can also try to do bottom to top, which again would be iterating over the array right to left. Doing repeated fix up, that is not going to work. That would produce an invalid heap, meaning the array would not properly represent a heap. You can also try top to bottom, which is iterating left to right, doing repeated fix down, and that would also produce an invalid heap, right? You just have to try it out. I'll let you try it with like these examples right here. It's not easy to do. After 2 or 3 steps, you'll be able to see it. Okay, it just won't work. Then the last approach that would work is to proceed top to bottom. So again, left to right, doing repeated fix up. That would work, but that would mean that it's no better than actually just sorting, right? So it would be n log n time, okay, which is the same as doing a sort. So why would you do that if you could always throw it to a sort algorithm and it makes no difference in terms of runtime? Then I would rather do that, right? But let's discuss, I guess, on Tuesday, because I flat out ran out of time, this approach in the second bullet on the slide, which is what we call heapify. In STL, this is the make heap function, okay? And it's not at all easy to see how this function works in linear time, which we're going to go over on Tuesday. So I encourage you to, also because you'll need it for project 2, hey, just declare an array, put in some random, like last lecture we discussed how you can use a random number generator to just create a large array with a bunch of random integer values. Then pass it to the make heap function, and then look at the array after, and then you'll see that the elements in the array will satisfy the heap constraint. Okay, so that's an exercise, and then on Tuesday we'll go over kind of the details of how that can happen and why we arrive at a linear runtime as opposed to nlogn. Okay. All right, so I ran out of time, and I do apologize. I'll try to get in touch with Xfinity, see if, it seems to be on their end. Honestly, I can't think of what was the issue here. So I apologize for the buffering interruptions. Get started on Project 2. Always, the earlier that you can start, the better. So, all right, you all have a great weekend. Stay safe. Let me see if there are some lingering questions that I could answer real quick. I think staff answered most of them. I don't know. By the way, who's in staff today? So I can thank who's on staff. Who's on the chat from staff today? Sorry, so that I can properly thank. All right. Well, whoever it is, thank you for taking care of the chat for the most part. I will sign off now. Have a great weekend. Where's my button?